homework on the board. We're going to do 32. Is there anyone who is confident at 32 and wants to do another work?
I can draw it out, but I can't explain why. Like,
I'm kind
the
of
answer is
confident.
something. I know the stoichiometry of doing it.
I'm kind of confident on that one. Do you want to look at it first?
I got all the right answers. That's all.
Are you able to explain this?
Kind of.
Why don't you try?
I can't.
Kind of. That was chapter 8, right?
I'll get it up on the screen.
Oh, perfect. Thank you.
This is the online book.
Oh, is that I can't go to
The link is in Canvas in the modules, but I think if you click it, it'll make you log in.
I'm going to go from the 35 grams, FeO3, and I'm going to use this to find my limiting.
Now, did you use either of the
Yes.
plots to do
Yeah.
the living? Okay, 'cause
Looked at, when you did it all
I
of
did
it.
all of them.
Which, for A, is more work than you had to do, but you then had the answers for the C.
Yeah.
Yeah. For C, you need to have the theoretical yield, which you already had.
So wait, you're finding the limit now?
Yeah, I'm finding the
She's trying to
limit.
figure out which, either the iron oxide or the HCl, which one is the limiting reactant. In order to do that, you start with 35 grams of each. She's taking 35 grams of iron oxide, figuring out how many you can moles or grams.
This is from moles, first one.
Okay.
So how I got this one here is because when I have the 2, did I do something wrong? Yeah, I did.
You started with iron oxide, but you're here. You
Oh
don't
wait, no,
have
I went
HCl.
down to the wrong one. Thanks.
So she's taking 35 grams of iron oxide. She's going to calculate how many moles of iron chloride she can make.
Then she does the ratio and then goes back to grams, right?
At this point, all we need is moles.
Moles.
So she doesn't have to take it all the way to grams right now. So she figure out how many moles of iron chloride her 35 grams of iron oxide will make. Then she'll do a second step, taking 35 grams of hydrochloric acid and figuring out how many moles of iron chloride she can make.
this is gonna be my theoretical, right down here, and then my limited is actually the smaller one, right?
So is that 4.44 or point? Okay, I couldn't see that point. So she figured out 35 grams of iron oxide will make 0.44 moles of iron chloride. She then figured out that 35 grams of hydrochloric acid will only make 0.32 moles of iron chloride. This is the smaller one, which means the HCl is her limiting reactant. Okay? Is that all you had for 8?
For A, did you, want me to do, wait, no, I had, yeah, for A, did you want me to do details?
Well, A, it says how many moles of each product will be
Right.
formed. So you now have to take your HCl and go to water. The water is 2 products.
Okay, that's why I had all 4.
Okay, so.
Yeah.
Isn't it?
I did all 4.
I didn't do extra work.
I did right there, so.
So now you need to go 35 grams of HCl to moles of water.
I was like, I had to do all 4.
So that means I'm kind of screwed up half the homework on, I think that was the same for a while.
So when she figured out how many moles of iron chloride she could make, she now knows that HCl is her limiting reactant. The question asks how many moles of each product. She already figured out the iron chloride, now she has to go back and figure out the water. Good. So,
Did you want me to do B and C too, or just?
do you want to do B?
If you want me to.
Go for it. Great. So the answer to A, how many moles of each product will be formed? 0.32 moles of iron chloride and 0.48 moles of water. You need to have both of them. Now she's going to do B.
Does anybody still need this before I erase it?
I do, because now I'm way lost.
Okay. Oh, wait, for a minute.
Outrageously.
Okay.
Well,
I was
that's
trying
the-
to,
That, but I didn't get that.
Okay. So, does someone else think they can explain it a different way? Someone who got the right answer.
help me.
Is my way difficult? Okay.
No, I'm not
So at this point, the first step was just a standard limiting reactant problem, right? Which is no different than anything we did in lecture last week, right? The only thing we did differently was we took it this one last step, because the question asks how much of each product, and there are 2 products. So in order to get that question right, we have to give 2 numbers. Okay? So she first figured out how much of the iron chloride she could make. She figured it out using both reactants. The question tells us we have 35 grams of iron oxide and 35 grams of HCl. She did 2 different stoichiometry problems, one from the iron oxide, which said we can make 0.44 moles of iron chloride. She did a second one, starting with 35 grams of HCl. Figured out that we can make 0.32 moles of iron chloride. This number is smaller than that number, so this is limited. So the first half of our A answer is 0.32 moles of iron chloride. But we have to figure out the second half, which is how much water we make. We don't have to do 2 different stoichiometry problems again. We already know from this that the HCl is limiting. So we do a stoichiometry problem going 35 grams of HCl to moles of water, which is 0.48. So the answer to A is 0.48 moles of water and 0.32 moles of iron chloride. Is there anyone is still questioning A? Okay. So then we can go to B. B, it says in part A, how many grams of the excess reactant remain? what is the excess reactant? Which one of these is the excess reactant? Iron oxide. We found HCl was the limiting reactant, so iron oxide has to be the excess reactant. All we have to do to figure out how much excess there was to do a stoichiometry problem going from 35 grams of HCl to grams of iron oxide. If we do that, we know we're going to get a number that's smaller than 35. Because we know iron oxide is in excess. We know that 35 grams is more than we need. So she's going to do the stoichiometry. She's going to get a number that is less than 35. That's how much we need. 35 is how much we have. So the difference between them is how much extra we have. That's how much excess reactant remains.
We're supposed to be on 3 on the HCl the second one. Is it not big enough? Wait.
No, you just,
Oh, wait, no, so.
HCl.
Yeah. Wrote it wrong, I think. Well, not wrong, that.
That should be iron oxide. Good. So, she did her stoichiometry. She found that 35 grams of HCl needs 26 grams of iron oxide to react. It's just a stoichiometry problem. No different than any other stoichiometry problem we've done that's grams to grams. She got 26 grams. We need 26 grams. We have 35. So 35 minus 26 is 9 grams. That's how much extra we have. And then C is asking us what is the percent yield. It says what is the actual yield in grams if the percent yield is 92.5. So what is the equation for percent yield? Actual divided by theoretical. So in part A, she just calculated how many moles of iron chloride she's made. For C, it says what is the percent yield in grams, which means her actual is in grams, so her theoretical is going to have to be in grams. But in A, she only had it in moles. So now she's just converting her moles of iron chloride from A into grams, which will be her theoretical.
Can you have it in moles though? Or is it always gonna be in grams?
You're going to have to do a moles to grams conversion either at the beginning like she's doing it, or you could figure out what but the actual yield was in moles based on the equation, and then convert that to grams.
So you still got.
You still got to
Yeah.
convert. It's just whether you want to do it at the beginning or the
Yeah,
end.
yeah.
Thank you. So if our equation was percent equals actual divided by theoretical times 100, okay? So we're trying to find our actual. So we need to have our theoretical. We knew our theoretical was 0.32 grams. That's right, 0.32 moles. She converted that 0.32 moles of iron chloride into grams of iron chloride. Okay? So now we had 92.5 as our percentage equals our actual divided by 52, our theoretical, times 100. When she solved for A, she got A equals 48.1 grams of iron chloride. Looks like several people are still writing. Okay. We don't really have time to do another big problem like this. Were there any of the multiple choice questions that got a lot of people?
The one that has the gain electron,
The oxidizing agent or reducing agent one?
number 2.
Yeah, I'm confused about this too. Yeah.
So,
Because in the video, you said something in the beginning, and then at the end, you said something else, and I was like, okay,
Yeah.
that's not what,
so
See, I hate watching the video, but I have questions, and I
who's
just ask.
confident in their
I think I raised
answer
my
for 2?
hand.
Hold.
So, if it's, if you look for the reducing agent, the thing that gets reduced, its number goes down, which means it gains an electron. So, the reducing agent has to lose an electron to give to the one that got reduced.
So the
Right.
answer is.
So you have to remember, reducing agent is the thing that gets oxidized. I warned you about that. Remember, it's backwards in your head. Where the reducing agent is the thing that gets oxidized. And if the thing that gets reduced gains an electron, that means the thing that gets oxidized loses an electron.
so the agent loses.
Loses an electron, right?
The reducing agent loses an electron.
Okay.
Yes.
Because the definition I wrote down was the reducing agent or reducing substitution causes it to gain an electron, which means the agent would lose an electron.
Right. So the reducing agent reduces something else. The other thing that's getting reduced is gaining electrons. So the thing that reduced it, the reducing agent,
So what was that point? Which one were you in?
There.
Some the other one.
2,
What was the
B.
Okay.
The reducing agent is the thing that gets oxidized. And if you remember that oxidizing is losing electrons, that means the reducing agent loses an electron. Make sure you have this down. Okay? You will see this again, potentially as early as 8:30.
Tonight.
Okay?
Which one?
2. Know what a reducing agent does, what an oxidizing agent does. The thing that gets oxidized, what does it do? The thing that gets reduced, what does that do?
So, let's say steel,
Mm-hmm.
okay? Air is gonna oxidize the steel. So air is the agent.
The oxygen in the air.
The oxygen in the air is the agent.
The oxygen in the air oxidizes the metal, so it is the oxidizing agent.
Right.
Yes.
The oxygen is the agent and the metal is the
The oxygen,
thing that's getting.
the oxygen is the oxidizing agent.
Yes.
The metal is the reducing agent. There are two agents,
Oh, no, okay.
reducing agents and oxidizing.
All right. I think so. Have to practice more.
If you don't have this, let's talk about it at break,
Okay.
okay? And other homework questions, we can talk about it at break. The quiz last week, I have them. If you weren't here Thursday, I have them. If you want them, make sure you can get them to you. There was the extra credit question, okay? The most common thing people said was they wanted to go over homework and quizzes, okay? That's definitely a good thing to do that. We need to be efficient with our time, though, okay? Not many people have been staying for office hours. There are some people that definitely take advantage of email. That's good. Everyone should be doing that, though, okay? I want to get too many emails that I have to start cutting them off. I'm nowhere near that still, okay? So email me, stay for office hours, ask me, okay? We don't have, fortunately, I would love to go through the whole homework in lecture. But we can't do that, okay? One or two people made the point of some people may be uncomfortable asking for help. They may not realize that a third of the class has the same question, okay? So what we're gonna do is, at least for the first next couple weeks, well, this week and then after spring break, see how it goes. I will plan to stay after lab to go over the quiz that you just got back that day. Okay? So you don't have to ask me to stay at that point. I will just plan to stay. It's up to you to, if you finish lab early, you just have to wait until everyone finishes. Okay? Because I'm not here during the day, it's not a matter of just stopping by and us going over it. Okay? I come straight from work to here, so the only time we can go over stuff is after lecture and after lab. Okay? I'm only here 2 days a week. Yeah.
Quick question on the homework that's going to be assigned for this lecture, since we're on spring break,
It'll be due next,
Tuesday.
yeah, Tuesday after spring break.
Okay.
I don't have any classes next week.
No, next week is spring break.
God.
It's just that because if you work, you realize, well, it's not really spring break.
Exactly.
It's not like spring break, yay, I can go on vacations. Yay, I only have to go to work this week.
It's like 2 extra days for homework.
Yay, I only get.
So, what I suggest doing in this class, you have to be active. You have to be an active learner. Take responsibility for yourself. Use me as a tool for you to learn what you need to learn. If you just sit here and expect what up here to all of a sudden make sense when you do homework, it's not going to work. And I think a lot of you have probably figured that out. You need to use the lectures as a tool to learn. Use me as a tool to learn. Use the book as a tool. Whatever you need to use it to learn what you need to learn. Okay? And if you're not getting something, you need to be active and go out and get it. Okay? So, is everyone still copying this stuff? Okay. So, we are actually, for the time being, done with chemicals. Okay?
Praise Jesus.
For the time being,
Remember, time being.
we are done with stoichiometry, I think, as far as I know. We are done with chemical single replacements and synthesis reactions, and things like things like that. We're gonna start talking about some things that you may or may not consider chemistry. And how many people have taken physics from high school or college? So today's stuff you very well may have done before, okay? We're gonna talk about specific heat and gas laws. Okay? Both chemistry and physics like to claim specific heat and gas laws as their own. So everybody teaches it, okay? We're no exception, so we're gonna go over it. We'll probably will not get through all the slides. After class or during the quiz, I'll amend the homework so that it only reflects what we actually went over. So the first part of today is energy. We talked about previously exothermic and endothermic reactions and processes. Okay? Does an exothermic reaction gain or lose energy? Exothermic. Loses. It gets rid of it. It releases it. Right? And we said that all chemical and physical changes have energy changes. Any chemical or physical change that you have will also have an energy change that goes with it. We said that exothermic reactions or processes release energy, and things that are endothermic take it in. They gain energy. They require energy input. Yeah.
On the homework, there was a question about boiling water.
Mm-hmm.
You're putting energy into the water.
Mm-hmm.
Okay, so isn't that endothermic?
Yes.
But it's also exothermic because you're releasing the gas.
But
That's what I'm saying. That's the
Yeah,
one in
I
the back
was
of the
really
book.
confused on that, that was something else.
I was like, that's kind of bold, isn't it?
I was going off the hand touching thing that
Yeah,
confused me.
I was saying the pot's really hot, so.
well,
The water's cooling.
I'm sorry.
so unfortunately, we're back into one of those
No, it says
subjective things.
endothermic.
It does say that, yeah. So the boiling itself, you know you have to heat it, right, to boil it. That is, you're putting energy into it.
Mhm.
The reason it feels hot to you is because as you're heating it, it's also cooling off. And cooling is exothermic, okay? But the net change, the most simplistic way of looking at it is you have to put the energy in to boil it,
So then,
okay? So it's really, you really have to look at the question. It's boiling. Boiling, you have to put energy in. You're ignoring the whole process of, yes, it's trying to cool down as I'm boiling it. If your hand was the same temperature as the boiling water, your hand wouldn't feel hot to you, because to you that would be normal at that point. Burning is exothermic. So if you put the boiling water on a gas stove, you have an exothermic reaction of the burning gas underneath that releases heat and then gets absorbed by the water in an endothermic process to boil. Ammonium nitrate dissolving in water is endothermic. This is what's in a cold pack. When it dissolves, it absorbs energy, which would be your hand or your skin or whatever, wherever that cold pack is touching, which cools down your skin. It's taking the energy from you into it, which makes it feel cold.
Is that the same reaction that happens with heat pack?
Heat pack is the same idea, it's a different reaction. That one is exothermic.
also, it actually sucks out your body temperature.
It's just a reaction that is taking in heat as it goes, and if you touch it, it sucks it out of you.
Wow.
If you put your hand on an ice cube, that's the same thing. It's melting, just like boiling. Melting is endothermic. absorbs heat to make it happen. If you put your hand on the ice cube, it sucks the heat out of your hand into the ice cube, it melts. This is our burning balloon again. I wish we could do it in here, but we can't. This is a balloon filled with hydrogen gas. Touch it with a match and it blows up. Okay? This is the hydrolysis we talked about before. Hydrolysis is endothermic. You have to put electricity into it. You have to put power into the water to break water apart into hydrogen and oxygen. This is endothermic. There are different types of energy. I think we've talked about this like the first week. There's kinetic energy. Kinetic energy is the energy of something that's moving. Okay? If I hold this marker perfectly still, it has no kinetic energy. Okay? When I drop it and it falls, it gains kinetic energy. Kinetic energy is not only of an entire object, but you can talk about the kinetic energy of the atoms and molecules that make up the object. In a solid, the atoms and molecules, they don't move around like a gas molecule, but they sit there and they shake, just back and forth in one place. As you heat it, as you increase the temperature, the kinetic energy of those molecules goes up, which means they're shaking faster and further. Eventually, they start moving so fast that they break away and become a liquid. And then they start moving around faster in a liquid, and eventually they get so much kinetic energy that they break away and become a gas. Okay? Temperature is actually a measure of kinetic energy. When you take the temperature of the water on the stove, you're measuring the kinetic energy of the water molecules. That is what you're doing. So the kinetic energy goes up as temperature is increased. There's also potential energy. This is stored energy, and it's only possessed by something based on its position. So I think we talked about dropping something. So if I have this marker here, it has no kinetic energy as a marker. The atoms do, the marker as a whole does not. Okay? It has no kinetic energy, it's not moving, but it has potential energy. Because you know if I drop this, it's going to fall to the floor, right? If I set the marker on the floor, does it have kinetic energy? No. Does it have potential energy? No. It can't fall.
You can kick it.
But kicking it is not based on its position. I have to do something to it to make it move at that point. If I hold it here, I don't have to do anything to it to make it move other than drop it, right? So here it has potential energy but no kinetic. At the bottom it has no potential and no kinetic. As it's falling, it's converting the potential energy that it had here into kinetic energy, right? The closer, when I drop this, the closer it gets to the ground, the faster it's going to move, right? So up here, when I first drop it, only a little bit of potential energy has been converted to kinetic energy. It's not falling very fast. Just before it hits the ground, all of its potential energy has been converted to kinetic energy. It's moving as fast as it's ever going to move. Then when it gets to the bottom, it stops. It has neither. If I throw it up, as it went up, it gained potential energy and lost kinetic energy. If I throw it, the higher it goes, the slower it moves, right? The fastest it moves is right when it leaves my hand. So as it goes up, all that kinetic energy gets converted to potential energy, but then it falls back down and the potential energy gets converted back into kinetic, and then I catch it, and then it has neither. It can now fall from here to here, but if I was throwing it from the ground up and I caught it on the ground, it would have no potential energy. There's also potential energy in the form of chemical energy. If you have two reactants, say the natural gas in the stove and the oxygen, If you mix them and they react, you're going to get energy. You don't have to do anything to them. They're going to do that. They're just going to react and give off energy. That is a form of potential energy. This is exactly what we were doing. This is a ball getting hit up. Kinetic energy goes, the ball is not moving, the hand hits the ball. The hand has kinetic energy. The hand transfers that kinetic energy into the ball. It then goes up, and all that kinetic energy gets converted to potential. Then gravity pulls it back down and converts it back into kinetic until it hits the ground. Here are a couple pictures of molecules. Which one would you say has more kinetic energy based on this artist's drawing abilities?
A.
Why?
Because of the length of the trail behind it.
Right.
So it's moving faster.
In the conventions of how we draw things, the longer the line behind it, the faster it's moving, right? So we look at this and we say these molecules are moving faster than those. The faster something is moving, the more kinetic energy it has. In reactions, we don't necessarily talk about kinetic energy. We're more concerned about what we call heat. Okay? And you're going to have to convince yourself that heat has a scientific definition that is slightly different than what the random person on the street would consider heat. Okay? To us, heat is a thing. Heat is not temperature. Heat is a thing. We can't see it, but we can measure it. We can see it by measurements moving from one place to another. Okay? It's just like mass. We can't see it. Heat is what we describe as energy that gets transferred between two things that have different temperatures. Okay? If I have this marker is room temperature. Say it's 20 degrees Celsius. And say my hand is body temperature, 37 degrees Celsius. If I grab this marker, where is the heat being transferred from and to?
From your hand to the pen.
From my hand to the marker. My hand has more heat, so it has a higher temperature. It goes to the thing that has the less heat, the marker, the thing with the lower temperature. In chemistry, we normally talk about heat in joules or calories. Okay? 1 calorie is 4.184 joules. I believe that is on here. Let me make sure. Yes. Yes. So on your cheat sheet, 1 calorie equals 4.184 joules. So you do not have to memorize that conversion. Okay? You just have to know that it's on here and be comfortable using it. Unfortunately, the calorie that we use in here is different than the calorie that's on the nutrition label. If you look at a nutrition label, calories has a capital C. Here, calories has a lowercase c. Calories with a capital C is a kilocalorie. It is 1,000 lowercase calories. Circle that. You will see that again. Okay? Remember, a calorie with a capital C is 1,000 calories with a lowercase c. If you see a problem that talks about calories, the first thing you have to do is look at whether that C is capital or lowercase. People who write exam questions like to try to trick you by putting a capital C, hoping you won't see it. Don't be that person that doesn't see that. Okay? You want the hardest part to be the problem itself, not seeing that the C is capitalized and not lowercase. So, this nutrition label from something that has organic whole grain wheat, organic evaporated cane juice, and natural flavor.
Sugar. Evaporated cane juice.
Anybody, what could that be? Whole grain wheat, sugar and natural flavor.
Cereal.
Maybe cereal. There's no nutrients or anything in it. I don't know. But here it says one serving has 190 calories with a big C. How many calories with a little c are in one serving of this?
0.18.
No. 190,000. One of these calories is 1,000 of these. So you take this number, multiply it by 1,000. Okay. You can do this with dimensional analysis. 100.
The red one was good.
Oh, I did want to say, for your videos, it's hard to see the black marker on the board.
The light is bright, and I can't see it.
Unfortunately, I can't figure out how to shut this off. Does that help at all?
I don't know. Have to see the video.
That's probably too dark, isn't it?
Yeah.
No, that's perfect.
So we started with 190 calories. What number goes here? I'm doing this in dimensional analysis. 1 calorie with a big C equals
1,000.
1,000 equals 190,000 calories. Now, how many joules are in 190 calories with a big C? Here we have that 1 little calorie equals 4.184 joules. So I'm going to take this as a starting point and convert this from calories with a little c to joules.
Oh, I didn't finish it.
So I have 190,000 calories. That's
784. Did you say 1 or 7? Did you say 7 or 7? Oh.
We abbreviate joules with a capital J.
Mhm.
So what number goes here?
1.
1 calorie equals
4.184.
4.184 joules equals
794,960
What he said.
divided by 1.
Is that correct?
Yes.
Does anyone want to say no?
No.
Why?
Sig figs.
Sig figs.
Only
Oh,
3.
it should be 3, so it should be 195.
7.94.
Well, 795.
So we started with 2 here, and then there's still 2 here, so this has to have 2, 790,000 joules. Still can't forget your sig figs. Unfortunately, sig fig is the thing that everyone hates, is the one thing that never goes away.
Did you do it in 10th power or no?
Yes. So if you wanted to do this in scientific notation, what would it be?
7.90002.
10 to 4.
1, 2, 3, 4,
Yeah, so
5.
I forgot to
Threw me off like that.
2.9 times 10 to the 5th joules. You cannot put these zeros here in scientific notation. If you do, then you're saying they're significant.
Okay, only if there's another number between the zeros. Like a whole number. Would be small. So it was like 1906.
It is a cereal.
Right, use the zeros at the end. There's no
Yes,
decimal.
1 serving of this cereal.
So we don't
Not a
count
cereal
as
I
a
would
single.
want to eat, I don't think.
If there was a decimal after the
And
zero,
kids,
it
it's
would
only a
matter,
single
but
label.
there's not.
So that's what we just did.
Like it was
Okay.
like zero.
The first way we're going to use
Then it's significant.
our heat is talking about specific heat. And specific heat does not mean a certain heat, like this specific heat as opposed to that heat. Okay? Specific heat is how much heat you have to put into something to change its temperature. Or going the other direction, when it cools off, how much heat does it release? When you put heat into something, its temperature goes up. You're adding heat to it. But when it cools off, it is releasing that heat. So, if I have a cup of water and I heat it up, I'm putting heat into it. If I then put it back on the table and let it cool to room temperature, it's going to release all of the heat that it absorbed. Say I put 5 joules of energy into it, temperature goes up, I let it sit there, it's going to release that 5 joules back out to get back to room temperature. You've probably noticed that some things heat up faster than others. That's because they have what we call a low specific heat. The specific heat is how much heat you have to add to increase 1 gram of something 1 degree. Okay? So, if you have something that has a specific heat of 1, you have to add 1 unit of energy, depending on the units, and we'll talk about that. Say your specific heat is in calories. You have to add 1 calorie to make 1 gram of that increase 1 degree. If you then have a different substance as a specific heat of 2, to make it go up with the same amount of temperature, same number of degrees, you have to add twice as much heat. So the units for specific heat are either going to be joules per gram degree Celsius or calories per gram degree Celsius. Okay? It's going to be important to look at the units here, because if the unit on your specific heat is joules, then our energy that we're calculating is going to give us joules. If our specific heat has a unit of calories per gram Celsius, then the energy that we calculate is going to be in calories. Water is 4.184 joules per gram degree Celsius. Does 4.184 look familiar? It's 1 calorie. The unit of 1 calorie was defined by how much heat you have to put into a gram of water to increase its temperature 1 degree. That is where that number came from. Okay? Which means, if you do all the conversions, 1 nutritional calorie with a capital C is how much energy you have to put into a liter of water to increase it by 1 degree Celsius. Okay? You don't have to worry about that. Just to me, that's kind of interesting that that calorie with a big C means something. It's how much energy you have to put into a liter of water to increase its temperature by 1 degree. This is just some examples of specific heat. And what I want to point out is that things that are metals, remember metals are on the left side, tend to have low specific heats. Here's gold, right? Aluminum, carbon, calcium. These are all very low, right? Come over to this side and pick out some things that are not metals. Water is incredibly high. There are very few things that have specific heats as high as water. Wax, oils, marble, they're all higher than most of these metals. In general, metals have low specific heats. You don't have to put much energy into them to make them heat up. and also when they cool down, they don't release much heat. We have an equation to calculate specific heat. This one is not on your cheat sheet. Luckily, it's pretty simple. There's only 4 variables. There's no divisions. It's just that equals that. Okay? So in this equation, delta H equals mc times delta T. Delta H means change in heat. When you see a delta like this, it's always going to be a change. A positive delta H means heat went up. A negative delta H means heat went down. That's telling us what it changed. So if we have a delta H, say it is positive 5, that means it went up 5. If we have negative 5, that means it went down 5. If we have negative 6, that means it went the same direction as my negative 5, but it went down further. Okay? So if delta H is change in heat, delta T is change in temperature. So remember, we're talking about specific heat, how the change in heat, how much heat we have to put in to change the temperature. So we have 2 things changing at once, the heat and the temperature. M is the mass of the object or whatever we're heating, and C is the specific heat. Specific heat will either always be given to you, or you'll be given the other 3 things and you have to calculate the specific heat. Specific heat for an element or a compound is not something you would know. It's either going to be given to you or it's going to be what you have to calculate. So let's do an example. We have 15 grams of water. It's at 25 degrees Celsius. You want to heat it to 75 degrees Celsius. How much heat do we have to add? First thing to do is take stock of what variables were given. There can only be one that's missing. If you're missing 2 variables, either you're missing it, it's not completely obvious, you have to sort of figure it out, or the question is wrong. If there's just 2 variables that are completely missing, you cannot do it. So, of the 4 variables that are up here, which one am I trying to solve for? Delta H. How much heat must be added? Okay. So, delta H. Delta H is what we're looking for. What is our M?
That's 15 grams.
15.0
grams.
grams times C. Now this is one of those ones that I was talking about. It doesn't tell us C, right? But we have to be given C. Yes, Ben.
That's 15.
Wait, yes. Yes. So we talked about, the reason it didn't give it to us is because it's water. Water is a set number. It's 1 calorie per gram. On an exam or a quiz, you would be given.
That's a number of cases.
So since we're finally, since it's in grams, we have to use calories, so it's not like the 4.184 units.
You can do either one. You can either do 4.184 joules, and then your delta H is going to be in the unit of joules. If you use the 1, your answer will be in calories. This does not specify which one you have to do. So either one would be correct.
So it's gonna be different answers, but either one is correct depending on how you do
Yeah.
it?
They're different answers because they're different units, but the 2 are equal to each other.
Oh, okay, got it.
It's like reporting something in meters or kilometers. If you do the conversion correct, they're the same exact thing. So, let's start with our 1. 1 calorie per gram degrees Celsius. That's our unit. times delta T. What is our delta T? 50. You have to make sure you have the right sign on your delta T. M and C will always be positive numbers. The sign, positive or negative on a delta T, is going to determine whether a delta H is positive or negative. So in this case, is our delta T positive or negative? Is it changing up or is it changing down? It's changing up. It's going from 25 to 75, so it's a positive delta T. Degrees.
Wait, 50,
50.
because you,
Thank you.
yeah.
50 degrees C. So to find our delta H, we just go 15 times 1 times 50, which is 750.
Yes.
50 calories. I could, just like Madison was asking, we can do the same exact problem in joules. In that case, delta H equals 15.0 grams times 4.184 joules per gram degree Celsius times 50 degrees Celsius. And that math I can't do.
Like 112 is when I did it
No,
earlier.
it's 3,158,
3,150.
8.92, so it would be 3,140.
How many sig? We need 3 sig figs.
Wait, did I do something wrong? I did something wrong.
Yeah.
Ignore that. It's actually
3,140.
3,140.
What is it?
15.10.
3138 goes to 3140 joules.
So both of these would be right?
That zero has to be significant, right?
Mm-hmm.
But that or that would be correct, because this does not say what unit our answer has to be in. So, the second point, we have 15 grams of water cooling from 75 to 25. What is the heat change here? What is our delta H here?
Negative.
It's negative, right? Temperature is going down. It's 75 to 25. As temperature goes down, is releasing heat. Is there an easy, quick way of figuring this out without redoing all of our math?
Put a negative sign in front of the 750.
Right. It's the same problem, it's just going in the opposite direction temperatures, right? So delta H equals 15 grams times 1 calorie per gram degree Celsius times negative 50 degrees Celsius, which makes our answer negative. That's the only difference. Same thing here. Put negative 50 makes our answer negative 3,140. This is just what I was saying. We take water, heat it up, and then let it sit back at room temperature. It's going to give back the exact amount of heat that we put into it. We heated it from room temperature 25 up to 75, let it sit there, it cooled back down. 750 calories that we put into it came back out. Not 749, not 751, 750, the exact amount that we put in. This one's going to make you think. Okay? Here we have a block of wax. We have 4 chunks of metals. They're all heated to the same exact temperature, and we set each one on top of the wax. Some of them melt the wax and sink further than the other ones. Which metal, A, B, C, or D, has the highest specific heat?
D.
So if you're good at taking exams, you can probably figure it out. It's not A or C, right? It's either the one that went the furthest or the one that went the shortest, right? So we're narrowed it down to B and D.
So it'd be D, correct? Because it has, the metals have this.
Takes longer to melt it.
Who said, just show of hands, how many say B? How many say D?
Wait, did you raise your hand for B or D?
Both. Just, it's a thing. If no, the person in front doesn't raise their hand, then everyone knows raises their hand.
I can see how it could potentially be D though, but I just find that.
Who wants to defend the answer B? Let's get Ben, and then if you don't agree with Ben, go ahead.
Well, if having the greatest amount, the greatest specific heat would mean you have to put more energy into it. So when it's being allowed to cool, it would give more off and melt more wax.
Do you agree, Holden?
I think so. I was gonna say that it was B because with the higher specific heat, that means it takes more energy to change the temperature. So B is gonna stay at the high normalized temperature longer than A, C, and D, and be able to drop faster for a longer period of time.
He's it better.
You both said the same thing. You're just talking about it in terms of heat, and Holden's talking about it in terms of time. But he's using what he knows about heat to talk about it in time. You both said the same thing. Who wants to defend D? No, nobody said D.
I still think it's D, but I'm not gonna try to defend it.
Okay.
I would think D is aluminum because it's dissipated so fast, and that B was probably gold or lead because it retained heat for so long.
Well, we're not trying to figure out which is which. So Ben and Holden are correct. B has the highest specific heat. High specific heat means that as it cools, it's going to release more heat. They all started at the same temperature, right? We heat them all to the same temperature. They're all eventually going to cool to room temperature, right? You know, if you put it on a cool block of wax, it's going to cool down, right? So, the thing that, if they're all starting at the same point, and they're ending at the same temperature, their delta T for all of them is the same. Does everyone see that? They're all starting at the same temperature, they're all ending at room temperature. So delta T is the same for all of them. It says they all have the same mass. So mass is the same for all of them. The only thing that's different between them is their specific heat. Whichever gives off more heat is going to release more heat into the wax. When the wax absorbs that heat, it's going to melt. So the thing that gives off the most heat is going to melt more wax and sink further. That's how Ben, I believe, saw it.
Yeah.
Okay.
It's metals.
Okay. The way Holden looked at it was the thing that has the higher specific heat has to absorb more heat to get back to room temperature. So it's going to take longer. So it's going to stay hot longer, and if it stays hot longer, it's going to melt further. Is that how you saw it? Okay. Yeah, sir.
You know, it might be confusing, because you had mentioned that metals have low specific heat, so people might be caught on that one metal might be denser than the other, so you keep saying higher specific heats with the metals, I think it's confusing.
In this case, they are all metals.
Right,
Right.
just some metals might have higher or lower, and
Yes, so
might be,
everything has different specific heat. In general, the metals are low specific heat. So if you had something that was not a metal, it probably would have melted all the way through. This is more complicated than you have to do on a quiz or an exam. But I like this because it makes you think about what specific heat really means. Okay? So if I have something with a high specific heat, do I have to put a lot of energy or a little bit of energy to make it heat up, to raise the temperature? A lot. If I have something with a high specific heat and something with a low specific heat at the same temperature, and I let them cool down, which one releases more heat? High specific heat or low specific heat? High specific heat. If we look at the units, it's calories per gram per degree Celsius. So what that means is for every gram that changes a degree Celsius, we get this much energy out of it. So if I had another one that was 2 calories per gram degree Celsius, that means for every gram that changes a degree Celsius, I get 2 calories. All of that energy I release goes into the surroundings.
So it doesn't really retain the heat, it's just because it's hotter, it goes down further.
It's not hotter, no. It starts at the same temperature. It has more heat.
Right.
That's the scientific definition of heat. So if something has more heat does not mean it has a higher temperature. If they're 2 of the same exact things that have the same specific heat, then it does.
So it's the same temperature, but it absorbs more heat.
Correct. It absorbs more heat to get to that temperature.
Right, okay.
It's like different price tags, right? If I want shoes from Payless and shoes from, I don't shop at any place expensive, so I'm just going to say Macy's, I don't know. I'm more of the Payless person. They're both pairs of shoes, right? To me, they're both pairs of shoes, which is why I shop at Payless and not Macy's. But I have to pay more to get the pair of shoes at Macy's than I would at Payless, right? So to get that temperature change, I have to pay more heat. But if I return it, I get more heat back from Macy's than I do at Payless.
Strangely, I followed that.
Big refund.
Shoe thing.
I strangely got that.
So this is just again what the sign of delta H means. Negative delta H means it's losing heat. When we said exothermic things lose heat. So delta H negative is exothermic. If something has a positive delta H, it's endothermic. Okay? We talk about the system and the surroundings. The system is what we're observing. Okay? It's going to be a block of metal, or it's going to be a chemical reaction. The surroundings is everything else. On the last slide, the surroundings was the wax. For a chemical reaction, it's just going to be the air around it. It's the beaker that it's in. It's the flask that it's in. Okay? In exothermic reaction, delta H is negative, heat goes out. We also use lowercase q for heat. Q, circle this. Lowercase q is exactly the same thing as delta H. Okay? It's just delta H more directly says it's a change in heat. Q is just saying heat. But Q and delta H are the same exact thing. In an endothermic process, delta H is positive, Q is positive, Q greater than 0. Heat is coming from the surroundings into the system. In the exothermic process, heat went from the system into the surroundings. The change in heat in the system is exactly the same, but with an opposite sign as the change of heat in the surroundings. Say in an exothermic reaction, the amount of heat that is lost by the reaction is absorbed by the surroundings. None is lost. In an endothermic process, however much the process absorbed the surroundings lost. Okay? It's just like money. You can't make money. If I'm selling something, there's a finite amount of money, right? So however much I gain or lose is how much you gain or lose. Here's another problem. Here we have aluminum. We're given the specific heat. It says we have 156 grams of aluminum at 75 Celsius, and we're cooling it to 25.5 degrees C. There are two questions here. How much heat is transferred, and what is the sign of Q, and what is the significance of that sign? So what is my equation that I'm going to use here?
Delta H equals,
Mass times calories times density.
Mass times C, in this case, this C is the specific heat, times delta T. Our question is, what is the sign of Q? How do I get Q from this?
Q equals?
Yes. Delta H is the same exact thing as Q. I'm going to say Q equals delta H, which equals M times C times delta T. So Q equals, what is my M? 156 grams. What is my C? 0.895 joules per gram degree Celsius. What is my delta T? It's not exactly 100. It's not. It's 25.5 now.
Negative 49.5.
Negative 49.5 degrees C. Why is it negative?
It's cooling, reducing temperature.
It's cooling, so the temperature is going down, right? We can take our final minus our initial is our change. Final minus initial equals our change. Our final is 25.5 minus our initial is 75 equals negative 49.5. To me, it's probably easier to not try to do this. You can look and say which direction it's going and how far it's going. If you really need an equation, you can do this. So when you do that math, what do you get? Negative 6,911. Okay. How many sig figs do we need?
4,
3.
3. Every number up there has 3.
So it'll be 6.11 times 10 years.
Negative 6,900. That is joules, because our specific heat had joules. If our specific heat had calories, our answer would have been calories. Yeah, hold on.
how many sequences are supposed to have?
Yeah.
I said 3 and then did. Thank you. So, we did our math. You have to answer the question, right? What's the first part? How much heat is transferred? How much heat is transferred here? 6,910 joules. In this question, it says how much heat is transferred. It's not even asking us what direction. So we can just give it. It doesn't matter that it's negative. 6,910. If I ask you this question and you told me negative 6,910, I would know exactly what you're saying. I would not mark you wrong. Okay? But the more correct number here is the absolute value of this. Whether it's positive or negative, we report it as a positive, right? It's like saying, if I sell something, how much money is changing hands? It doesn't matter what direction it's going. Whether I'm selling it to Michael or he's selling it to me, it doesn't matter what direction it's going, the same amount of money is changing hands. That's how much heat is transferred. Second part is, what is the sign of Q? Negative. And what is the significance of that? Negative. It means it's going down, which means what happened to the heat? Where did it go? To the surroundings. It was released from the system into the surroundings. So is this endothermic or exothermic? Exothermic. Yeah.
How do you explain something that's radioactive?
Not with nothing anywhere similar to this. In a whole other class.
Like gives his own heat and releases his own
No,
heat.
like a senior level college class. That's how
Yeah.
you explain it.
Okay.
Here's another one of those thinking problems. We have 50 grams of 3 different metals, aluminum, copper, and lead. We add 1 kilojoule of heat to all of them. Which one increases temperature the most? We can eliminate copper, right? Because it's in the middle. Who says aluminum? Who says lead? Who wants to defend their answer? Ben.
I think it's lead because it takes less joules per gram to increase temperature.
Right. So specific heat means how much energy you have to put in to change it a degree. So something with a low specific heat has a low price tag. If you put the same amount of energy into it, you're going to get more back in terms of change in temperature. So if you put the same amount of energy into aluminum and lead, then this one, a change degrees Celsius costs less. So you get more degrees Celsius out of what you put in. This one, our temperature change costs more, so we get fewer degrees for our heat. Does that make sense?
So if you did use 1 kilojoule, oh, never mind, I wasn't counting for the 1,000. What if we just did 1 joule?
If you
That
did-
would do it better. And then we could say that lead would change around 10 degrees Celsius.
Well, let's completely simplify the problem. That's where you're going. Let's simplify it even further.
Okay.
So say we have 1 gram of each thing, right? And we put 1 joule in. Aluminum takes almost an entire joule to go up 1 degree. So aluminum, let's say it goes up 1.2 degrees Celsius, something like that. For lead, it only takes 0.13 joules to go up a degree. So I'm going to say that's about an 1/8. Okay? So lead is going to go up about 8 degrees. Okay. Let's look at it another way. If we have 1 gram and we change the temperature of each one 1 degree Celsius, how much energy do we have to put into the aluminum to do it?
0.95 joules.
Right. 0.895 joules. That's what the specific heat means. We have 1 gram, we change it 1 degree Celsius, it takes 0.895 joules to do it. for our lead, how much energy do we have to put into it? Change 1 gram, 1 degree Celsius.
0.129 joules.
0.129 joules.
Now, that's constant, it doesn't matter like how thick the lead is or anything like that.
Nope. It's, because the thicker it is, the higher your grams will be. It's like density, it doesn't change. If you have lead, it is this.
Okay.
This is not something to be testing on, but just sort of interesting. Proteins, fats, carbohydrates all have X amount of calories per gram of them. Okay? Both proteins and carbohydrates give you 1 kilocalorie, nutritional calorie, or however you want to do it, calorie with a big C, for every 4 grams. 4 grams of protein will give you 4 calories. 4 grams of carbs will give you 1 gram of carbo, I don't know what I just said. 1 gram of protein will give you 4 calories, nutritional calories. And 1 gram of carbs will give you 4 grams, 4 calories. I'm just going with the next slide. You don't need to know this, it's just interesting. But fats have more energy per gram, which is why fats make you fat, right? Taking in more energy. Okay. So that is specific heat. Any last questions on specific heat? Okay. We'll take a break before we start our gases, and we'll start at 7:40 on this clock. Don't forget to turn in your homework if you're done with it.
Homework on,
Turn the worksheet down. As soon as you get the other stuff done, we expect that to be tonight. If you get it to me before midnight, after midnight, and up until Thursday, it's 1 by 3.
I don't know if positive like that. It doesn't oxidize.
The part that you turn in today will not be
Because when
considered.
you,
Only the part late.
I got no car for my life, but. I mean, I got
I
some
don't know, if it's oxidizing, it's reducing agent, then it's losing, right? Oxidize is reducing, I thought reducing, hold on. There's a reducing element is what is taken, and oxidizing is taken. But again, is a reducing agent. A reducing agent loses an electron, which is an oxidized element. So I'm happy.
Well, no, because that means there would be this one, so if it,
Yeah, that's, you're right.
if it gains an electron, it,
Yeah. I don't know.
nobody knows.
So that's not very far.
That's right.
Yours? It's making sense.
Because it would have gained when it gains the charge.
Yeah, you're right.
What about here?
2.3.
Here?
That's
They
it.
scanned it, so it's here.
Yeah, I see.
Wait, why? Print it,
6.36.
and then write on it, and then.
It's 1 mole, it's 2 moles, and then you see it. Yeah, because there's only, the coefficient is 1, but there's 2 in ACL. But 1 mole of that is whatever the mass of that is.
Shrinks, silver, and yellow gas.
And then I got it B.
Oh, you know what, I may have done it 1-to-1, because if it was 1-to-1, green is what I had. It would have never been divided, or it would have never been multiplied by something.
Yeah.
That's why I messed up. And then this guy here. Oh, you're here. Look at that. Weird.
See, how'd you get exothermic there? I thought it was endo.
I don't remember here, but that's what we. This gives off heat, right? Exothermic gives off heat. So, did just one?
Exo outside, so it like releases. Yeah, that's what I thought.
This one? Why? Doesn't that mean it's gaining heat? Hydroxide? I'm looking at it backwards then.
So,
Yeah, I think so.
iron hydroxide is insoluble. Iron plus hydroxide. Hydroxide is insoluble. It makes it really
Releases heat, right?
Just like water, like water, like water, like,
Goes up.
you know, what, like, just like the last hallway.
This one is like-
And then by the, you
See,
know,
20 minutes, I'm such a spin, so fun.
This one, it gains energy, that means it gains heat, so it stands up, right?
Well, that's convenient. Okay, you can just put it in here.
Yeah, no, I'm sorry, I was shaking my head, yeah, sorry. Realizing how stupid that mark was.
This one,
I know these are right because we're talking about it.
3.4 moles.
So,
Moles.
okay, compare.
So it's 3.4.
Put C for this, right?
Let's put A.
A lot of people do that.
The C.
That one is right.
I think it's
really confusing.
This one. I think we went over something.
This is.
He has good
Yeah.
I mean,
Which means it gains electrons, right?
These are a little more complicated. Hey, these change percents of the reactants. Assume 100 is
no, it's not. This one is
hydrogen, oxygen, by them by the molar mass,
This one is.
nitrogen oxide. So you figure how many moles nitrogen, how many moles oxygen you have. Take the smaller one of those two numbers, divide it in both of them,
So it might be the same thing
and
as
then get
numbers.
numbers.
But plus one?
I think this one was
Because you, because
203.
This one is oxidized.
That would be right. I think you got a 1 for N, a 1.5 for O. But you have to have all numbers.
something's oxidized, it gains electrons, right?
No,
N2O3.
the
In that case, N2O3 has molar mass of 76. You see also it's
oxidation. So it gets positive.
Yeah, so it was the worst.
So plus is right.
So I was,
That means it have a positive charge.
But
Ow.
the,
so here, it should be,
oxidized.
O10 is 14, O is 16.
Okay.
I don't know.
No, I think. Because, okay, reducing.
Right.
Reducing agent loses electrons because it gives electrons to the oxidized agent. On electrons have a negative charge. Or positive, electrons have a positive charge.
If you lose this electron, then it has positive charge.
Well, now this has a positive charge, but since this gained an electron, will it have a negative charge?
This one is electron.
Yeah.
This one
This
is
is the big one.
This is negative charge.
Multiple choice are 3 each.
I was confused between
Because I normally get first credit.
This where I had no.
Really, because it doesn't work.
I'm putting the star next to that.
and then for
I know what I did wrong here, it just took me a second.
That one, that one,
Because there's still remaining oxygen.
plus this one.
I put C because you still have oxygen remaining. If you count them,
yeah.
there's still oxygen remaining.
three, four, there's five of these, there's her, three, four, five, six, seven, eight. So there's enough, hydrogen to bond to the oxygen. But you're still remaining with this cell of oxygen, so there's a +2 for oxygen.
Oh, sorry. What did you get for number 3?
Is it the booklet?
No,
She hasn't done this one, that one yet.
Is it that, or is it the booklet? Oh, this is last week's. I haven't done this one yet. He did. Emmanuel, on the handout, what'd you get for number 3?
The one with that turn and
Yes.
Then they positive.
C? With a C?
I got C, and I don't know if I'm right.
I was confused between B and C.
The reaction.
No problem. This one is
I would say, yeah, it's a metal because it's oxidized, right? And
What's the
it
question?
refers to the reaction.
Can I see yours?
The reaction's gotta be positive because it loses 2 electrons.
When you lose them, you get a positive charge, right? So that's why I put that one.
Yeah, so I put that one too.
it's like reaction.
See, I understand this when I look at the graph, like when they say the temperature goes down, like, oh, I'm thermodynamic, but when I look at the graph, I guess because I'm looking at this as temperature.
NA doesn't do anything though.
If the graph goes down, it's excellent. If the graph goes up, it's negative.
CL
Look at it
does.
like this. If it goes up, it's
CL, you're, yeah.
Are the gas. How many people have done gas laws before?
That's what?
Gas law.
sounds like
Does PV equals nRT sound familiar?
Yes.
Then more people have done gas laws than think they've done gas laws. Okay. A lot of this gas law stuff is logical. Okay? It's stuff that you know, you just don't think of it in the scientific sense. If you heat a gas, what happens to its volume? It expands. You know that, right? If you take something that has gas in it and you compress it, what happens to the pressure in that thing?
It goes up.
It goes up. You know that, right? Most of what this is stuff that you know in everyday life, putting it into words and equations. We forget about gases, but gases are everywhere around us, right? If I go like this, I can sort of feel air, but it's like it's not even there, right? So we forget about it. The air around us is mostly nitrogen, fair amount of oxygen, 1% argon, and then a whole bunch of little stuff that doesn't really matter. Unfortunately, the CO2 is becoming more and more important, but that's not for this class. We talk about densities in terms, talk about gases in terms of densities. Compared to the other forms of matter, liquid and solid, what is the density of a gas? Less. Gases have very low density. If I take a sample of gas, sample of air, it's not going to weigh very much. In order to understand why these things happen to gases, we have to be able to think about them at the molecular level. You need to be able to picture little molecules flying around and how they behave at the molecular level changes and determines what we observe at our level. Okay? gases are molecules or atoms. Particles. If you just say particles, it doesn't matter. They're little things flying all around. For the most part, they're not close to each other. They're low density, so that all the particles are far apart, and they're all just kind of flying around. They move really quickly, really quickly. An oxygen molecule moves at 980 miles an hour. That's fast, right? But if I were to release oxygen here, in the front of the room, how long do you think it would take to get to the back of the room? Would it be, if I was moving 980 miles an hour, how long would it take me to get from here to there?
Not long.
Not long at all, right? If I opened that bottle of what, Macho aftershave or whatever it was in the lab, if I opened it here, there's gas molecules that are going to come off of that. How long would it take for you to be able to smell that in the back? It would take minutes probably, or at least seconds. A lot longer than it would take me to get from here to there if I was moving 980 miles an hour. So, if gases are moving this fast, why does it take so long for the aftershave to get from here to there?
Because the size of the atom.
Well, if I'm this big and I move 980 miles an hour from here to there, and all of a sudden I touch a Koopa, and now I'm little Professor Young, and I'm running from here to there, at 980 miles an hour, I get there at the same amount of time, right? It doesn't matter how big I am, my speed and velocity is the same. So why does it take the aftershave so long to get from here to there?
Because there's less amount. Because of the
They
compound
bounce
it's
around.
carrying.
It bounces around. This is a speed. If you've taken physics, you may remember the difference between speed and velocity. We're not going there. But this is just a speed. It doesn't tell us that it's moving from here to there at 980 miles an hour. They move randomly. So I'm trying to get from point A to point B, but I go to point C to D to E to F to H to G to back to A, all over the place. Eventually, I happen to get over there. That's why it takes the aftershave so long to get from here to there. I take that cap off, and eventually, it's going to be throughout the entire room, right? I'm going to smell it here, and I'm going to smell it back there. Because at that point in time, some of the molecules are here, some of them are back there. Half an hour later, the ones that were back there may be up here, the ones that were over there are now over here. They're just randomly moving around. Yeah.
When they change direction, does it need a large surface, or can it bounce and change direction off one other gas molecule?
Is that the next bullet point?
Okay.
Yes. So, they bounce off each other. They're a long ways apart, but they're moving so fast that they do hit each other. Because, I mean, if one molecule is here and one's here, at 980 miles an hour, it's not going to take long for that distance to close for them to hit, right? When they hit each other, they don't affect each other other than bouncing off each other. They hit and they bounce. So you can imagine, if you have a ball pit, okay? Imagine the balls in the ball pit are gas molecules, and you have another one that's trying to move around through there. It's going to take forever, right? They don't really affect each other, but they all get in the way of each other. But they're all moving really fast, but to get in our distance from point A to point B takes them a long time. When they hit, they don't stick. This is important. Gas molecules and atoms do not stick together. It's like they don't know the other one exists. They hit and bounce, and that is it. And one thing you already know is gases will expand to fill their container, right? So the density of a gas, how far apart the molecules are, is in part determined by how big the container is, right? if I take 5 gas molecules and put them in this bag, they'll be a certain distance apart. If I then put them in the trash bag, they're going to expand to fill the trash bag, and so the same 5 gas molecules are going to be further apart. You also know gases expand when you heat them. That's why if you have a can of Cheese Whiz, it says do not heat, right? Because it'll blow up.
See, I thought that was because of the metal can.
Because what?
The metal can.
Well, the metal can adds to the danger of it exploding. Then you have metal shrapnel. If you have something that's not going to make shrapnel, then it's not a big deal. Why, when you heat the gas, does it expand? If you heat something, temperature goes up, right? What did we say about temperature and kinetic energy?
When it goes up, it moves faster.
Higher heat means higher temperature, which means higher kinetic energy. Kinetic energy is energy of motion. So the higher the temperature, the faster the molecules are moving. Okay? If they're moving faster, they're going to spread out faster. Okay? That's why if I take my matcha aftershave and I heat it, it's going to get to the back of the room faster. They're going to move faster, they're going to spread out faster. Looking at these two pictures, you have a cool gas and a warm gas. Which one has the higher or greater density? The cooler one. There are more molecules in a given volume in the cool gas than the warm gas. So the cool gas has a higher density. Why does a hot air balloon rise?
Because the molecules are lighter than the air.
They expand the gases.
The gases expand, so they have low density, which makes them lighter than the air. Okay? So, when we did our graduated cylinder with the cork and the oil and the water and all that stuff, the thing that was the least dense floated, right? We're more used to floating in terms of liquids, in solids, things like that. But the same exact thing happens when you mix gases. Here, the air, the sky, the atmosphere is a certain density. If you heat the air in the hot air balloon, it expands. Extra comes out the bottom and the top. So the air in the balloon is heated. It is now the low density thing. So you now have a low density balloon in a higher density air. The low density thing floats up. Just like an air bubble in water. It's the same exact thing. We also talk about pressure of gases. You know tire pressure, right? When you have a flat tire and you want to increase the pressure, what do? You add air, right? So you add air, the pressure goes up. What happens when you fill your tires in the winter, when it's 24 degrees on Thursday night, and then it's 80 degrees on Sunday? What happens to the pressure in your tires?
Pressure goes up.
Pressure goes up. Did the amount of air in your tires change?
No.
No. So there we did two different things to change the pressure, right? We'll come back to this. When we change the pressure and the amount of a gas, and or the amount of gas, we change how that gas behaves. When we add air molecules to the tire, what happens? We said the pressure goes up, right? What happens to the volume? Say we're starting with a flat tire. When we add air molecules, what happens to the volume of that tire? It's going to increase until it's no longer flat, right? then what happens? The volume stops changing, but we're still adding air. So then what changes? Pressure, which is determined by density, yes. Because the volume is staying the same, we're adding more air as the density goes up. But our pressure goes up also, because our density went up, okay? So as you add it, the volume's going to go up as long as that's the first thing that's going to go up. If the volume can't go up, then the pressure has to go up. Which is why tires will explode if they heat too much. The pressure all of a sudden is too much for the tire, so the tire actually then expands when it shouldn't expand and blows up. Here's a weather balloon. What's making that balloon inflate when we add probably helium to it? What makes it inflate? What makes it blow up?
The molecules pushing out.
Yes.
Bouncing around.
Yeah. So you put the molecules in there. Here in our picture, these are our helium molecules, particles, or gas particles. That's the wall of the balloon. If we put more and more particles in there, there's more of them bouncing around. If a particle hits the wall of that balloon, it stretches it out, right? If you put just something in a balloon and bounce it around, when it hits, it's going to stretch it a little bit, right? The gas molecule does the same exact thing. It's just so small that it stretches it so little that we can't see it. But if we have a whole bunch of gas molecules, it makes the thing expand. We can't see each little punch from the inside, but we see the thing expand, right? And so, those molecules hitting the side are what actually determine pressure. The pressure in that balloon is pushing the walls of the balloon out. When that happens, the balloon expands. As the balloon expands, there's getting to be more and more and more surface area of the balloon, which means fewer molecules are hitting any given place. Also, the walls of the balloon get further and further apart, so the molecules actually hit the wall less frequently, right? If you take 1 billion gas molecules and put it in a little balloon, they're going to hit the walls really often. If you put them in a big balloon, they're not going to hit the walls as often. If they're not hitting the walls as often, the balloon stops stretching. So it will stretch until the point that they stop hitting the wall hard enough and fast enough to make it expand. Okay? Right. And so, if I then take this balloon and I heat it, I don't have more molecules hitting the side of the balloon, but now they're moving faster, so they hit it harder, which makes the balloon expand.
So that's what happens when you put the match, or what, the balloon with the match and it blew up.
What that was actually that's a reaction.
That's real. It's not that. It's
No,
not,
no.
It's not the.
Well, what happened there is the match melted the balloon, which released the hydrogen gas, which blew up.
Okay.
Yeah.
If you had the speed of those helium molecules, and you, like in miles per hour or something like that, you converted it to say feet per second, and then you had a super camera that could match that number of feet per second with frames per second. Could you see little variations in the wall of the balloon if you were taking photos that fast?
Yeah. They're going to be incredibly small.
Yeah.
Because I mean, one gas molecule is going to move like one latex molecule just a little bit in the balloon.
Oh, that's true. So it wouldn't be like big movements.
No.
Either.
No, it would be tiny, tiny little movements. There's just so many of them that combine to make the balloon expand. Pressure is an easy equation. Force divided by area. Okay. You won't have to do these calculations. Okay. But you need to know what pressure is. If you don't understand what pressure is, you're not going to understand what we do with pressure later on. Okay. But pressure is force divided by area. When we're talking about our gases, our pressure, our gas pressure, is the force of the gas particles divided by the area of the container. It's the total amount of force supplied by all of the gas particles combined divided by the total area, the surface area of that container. Okay? So if I keep this force constant and I make my container bigger, what happens to my pressure? It goes down. If I increase the bottom of my fraction, my pressure is going to go down. Okay? The pressure is the same thing with this pressure and the gas pressure.
Last slide.
Sorry?
Could you go back to the last slide? It didn't print out.
No equations aren't on the slide.
It's possible I deleted them. Depends on the mood I was in when I was
Oh, they
making
don't
these.
need that, delete.
Like, make them.
Oh, it's.
Thank you.
Got it? So if pressure is force divided by area, which finger hurts?
Oh.
The one with the least area. The hurting, the pain comes from pressure. If you know your Newton physics, you know that there's the same amount of pressure on both fingers. I'm sorry, the same force on both fingers. But here, it's spread over a tiny little piece of skin. So your pressure is really high. Okay? That's why, if you hit a nail, you hit the flat end, the pointy end goes into the wood. If you hit it that way, it's not going to work very well. It's probably going to fly out, and if you're not wearing safety glasses, it's going to hit you in the eye.
You can have a lab on that?
Huh?
No.
Here, but in both cases, you're going to hit the nail with the same amount of force. But here, all that force gets put on the head of the nail, so it's a high amount of pressure that goes into the wood. Here, the same amount of force is spread out over a larger area. That pressure is lower. It's not enough to make it go into the wood. You can imagine, though, if you were to hit this hard enough, it would go in. There's X amount of pressure that you need to get to make a nail go into wood. You can either apply a small amount of force on a small area or a large amount of force on a large area in order to get the same amount of pressure.
So the top of the nail has the lower pressure?
Yes, that top now.
Yeah.
The larger area has lower pressure. Here's two pictures. If we assume they're at the same temperature, which gas has higher pressure? Why?
It's more molecules.
More dense, because there's more molecules, which means that even though each molecule hits the wall at the same force as these molecules, there's more molecules hitting that wall. So your force, total force, is higher. If I take this metal can and I hook a vacuum up to it, you know it's going to crush. Why does it crush?
It's a negative pressure on the inside.
The pressure on the outside is greater than the pressure on the inside, so it's a short.
Right. So, in a normal can, empty plastic bottle around here. Here's a can. Right now, there is air outside the can and inside the can, right? The air inside the can is hitting the walls of the can on the inside, pushing out. The air on the outside is hitting the outside of the can, pushing in. But because there's a hole here, the pressure equilibrates. The pressure on the outside is the same as the pressure on the inside, which means the little gremlins on the inside are pushing the same force as the gremlins on the outside, and so the can doesn't do anything, right? If I suck the gas out of the can, now all of a sudden there aren't little gremlins in here pushing out, so the ones on the outside now crush it, right? It's just forces, just It's like having a tug of war. It says here they're pushing instead of pulling. If there's fewer people on the inside pushing, people on the outside win and the thing crushes. Well, I'm guessing that Doritos bag is not recyclable. We measure pressure in several different units. Okay? One you probably heard of is PSI, pounds per square inch. Okay? I know you scuba dive. Anybody else scuba dive? Anybody use gas tanks in at work or anything with a regulator on it? You probably measure it in PSI, would be my guess. The regulator probably has multiple units on it, but you probably read PSI, right? PSI means pounds per square inch. That is 1 pound of force. A pound is a force. That's one pound of force for every square inch of area. We said pressure was force divided by area. Here's our unit. Force divided by area. Okay? So one unit we use often is PSI. Okay? I'm going to come back to that. Here's some other units we normally use. If you look on barometric pressure, on the weather, they're going to tell you inches of mercury. Okay? Not PSI. It's still a measure of pressure. You're measuring the same thing, it's just a different unit. In science, we use a lot of times millimeters of mercury. Same thing, different unit. A millimeter of mercury is the same exact thing as a torr. Circle that on your slide and make a note of that. 1 millimeter of mercury is the same exact thing as a torr. Okay? Where these inches and millimeters of mercury came from are how we used to measure barometric pressure. If you take just a dish, fill it with liquid mercury, set it out, and then put this glass tube there. Okay? That tube is like a graduated cylinder. There are markings for barometric pressure to be inches. So there'd be 1 inch, 2 inches, 3 inches, 4 inches. The higher the atmospheric pressure, the more pressure pushes down on this liquid mercury and forces it up here. So at a high atmospheric pressure, you have high force here, pushing this up, which gives you a large number of inches of mercury. When the barometric pressure falls, the inches of mercury falls because there's less force pushing down here. Okay. But of course in science we don't use inches, we use here in this case millimeters. Okay. Very precise. We could use centimeters, but centimeters are bigger, so it's less precise. Okay. Another unit we use a lot is atmospheres, ATMs. We're going to use these a lot. Okay? An atmosphere is roughly the normal atmospheric pressure. Okay? 1 atmosphere is 760 millimeters of mercury. 1 millimeter of mercury is the same as a torr. So 1 atmosphere equals 760 torr. And there's also another unit of pressure called a Pascal. 1 atmosphere equals about 101,000 pascals. On here, this gives us conversions. It says 1 atmosphere equals a number of kilopascals. 1 atmosphere equals 760 torrs, equals 760 millimeters of mercury, and equals 14.7 pounds per square inch. So you don't need to know these conversions as long as you're comfortable using this. Okay. We need to do some practice conversions. Okay. Here we have pressure of our gas, 8.25 times 10 to the 4th pascals. We need to convert that into atmospheres and torrs. One of those is the logical first conversion to do. Which one do you want to do first? What unit are we starting with? pascals, we will have to go to atmospheres and torr. Our conversion factors make it very easy to do one of them. Which one is that? Atmospheres. To get to torrs, we're going to have to go through atmospheres. So might as well do atmospheres first. So I have 8.25, that's 10 to the 4th pascals. I'm going to use dimensional analysis. Pascals and atmospheres. And before I forget, you may sometimes see atmospheres in capital letters. It's the same exact thing. ATM. What number goes here?
101,325.
101,325 equals how many atmospheres?
One.
1. So what does that come out to be?
8.25 times 10 to the 4th power Pascal divided by 101,325.
Right? Which is?
8142.
814. We only need 3 signals. For 814 atmospheres. So that's the first part of my problem. Second part, I now have to take that to torr. So I'm going to take 0.814 atmospheres. Atmospheres, torr. What number goes here?
1.
1 atmosphere equals 760 torr. 0.814 times 760 equals 618. So it rounds down.
Yeah.
618 torr. Everybody have that copied? Yeah.
The original Pascals would be 82,900, right?
What?
First measurement, 8.25 times 10 to the 4th power Pascal.
That's 82,500.
82,000. Oh, 500.
Okay.
When we get into gas laws, there are certain variables that are going to keep coming up. We're going to talk about how they all relate to each other. First is volume. You're familiar with volume. In gas laws, we measure volume in liters. You're not going to want to use anything other than liters. Pressure. Normally, we measure it in atmospheres. Temperature. You're going to measure temperature in Kelvin. If you don't remember how to convert temperatures, you're going to get plenty of practice now. And we talk about an amount of particles which we measure in moles. These 4 things are going to determine the properties of a gas. And we talk about these gases as ideal gases. Okay? It's sort of like classical mechanics or Newton's laws. For us, in our normal everyday lives, they match what we see perfectly. But theoretically, they aren't 100% correct. So for us, gases behave a certain way. They behave like an ideal gas. Okay? And if they behave as an ideal gas, we can predict relationships. Okay? We're going to see if pressure doubles, volume halves. If temperature doubles, volume doubles. Okay? So perfect ratios. You have to assume the gas is ideal for that to be accurate. But in our world, that's close enough. If we take a weather balloon and we release it, it goes up in the atmosphere, right? What happens to the pressure outside of that balloon as it goes up?
Starts reducing.
It starts reducing. So what happens to the balloon?
It expands.
It expands until
It bursts.
it pops. Eventually it can expand no more, so it blows up, right? If you have a bubble,
No balloon heaven.
no balloon heaven, I guess. If you have a bubble at the bottom of the ocean is incredibly high pressure, right? If you have a bubble down there and it floats up through the ocean, what's going to happen to that bubble as it goes up? It's going to expand, just like the balloon did going from surface level up into the sky. Looking at this graph, without getting too detailed, what is the relationship between volume and pressure? The volume is on the y, and pressure is on the x.
As volume goes
As
up,
volume
pressure
increases,
goes down.
pressure increases.
So you can look at it either way. You're both correct, right? As pressure goes up, volume goes down. If I take a balloon and I can push on the whole thing and compress it, I'm adding pressure on it, the volume shrinks, right? If I look at it the other way, as volume goes up, pressure goes down. If I take a balloon and I somehow stretch it out myself, the pressure on the inside is going to go down. Because now all of a sudden the gas molecules are further apart. Just like if you take a syringe and you cover one end of it and you pull the plunger back, it pulls back because you're decreasing the pressure to the point that you create a vacuum. It wants to pull it back. Just like this. This is a piston and a cylinder. Okay? If the piston is here, the gas molecules are at this density and this pressure. If I push that piston down, what happens to my density of my gas? It goes up. What happens to my pressure? It
Increases.
pressure goes up. If I take something, if I take a syringe that's full, and I cap the bottom, and I try to push, it gets harder and harder to push, right? As you compress it, the pressure goes up, which means it's pushing back on your hand harder. This is assuming temperature doesn't change at the same time. We'll talk about how pressure affects things later. Let's look at this graph. Okay? What happens to the pressure when the volume is doubled? So here we're going to go from a volume of 1 to a volume of 2. Here are, how is that temperature?
Does it begin at a lower volume?
We'll do it both ways. Assume this is pressure on the x, okay? It's going up. Here, we're at 100, say 100 atmospheres of pressure. Here, cross that slide out, please. I'll delete it later.
Too late, we've already printed them.
Just cross it out.
What has been seen cannot be.
What you're supposed to get out of this.
It can't be unseen.
When you have your pressure, volume doubles. If you double pressure, volume halves. They go in opposite directions to the same ratio. Okay? If the volume goes up by a factor of 2, pressure goes down by a factor of 2. If pressure goes down by a factor of 2, volume goes up by a factor of 2.
So they're 1 to 1?
It's a 1-to-1 ratio in change in opposite directions. And we put this in Boyle's law. There's going to be a whole bunch of laws. There's Boyle's law. This little symbol means proportional to. So that's saying pressure is proportional to the inverse of volume. That means it goes in a 1-to-1 ratio in the opposite direction. If we rearrange this, we see that pressure times volume is constant. For a sample of gas, pressure times the volume will not change. If volume goes up, pressure goes down, 1 to 1, so when you multiply them together, nothing changes. Okay? If we do some algebra, we rearrange it, we can create a new equation that will tell us how pressure and volume change when we change one or the other. And that is P1V1 equals P2V2. The ones are before, twos are after. You have two sets of conditions, the before and the after. If you're given a starting pressure and a starting volume, given a final pressure, you just do the algebra to solve for the missing variable. Okay? I've already done the rearranging for you here. If this helps you with your homework, great. This gives you one form. You need to be able to do the algebra to rearrange it yourself. Okay? You can either rearrange it with variables to find the equation you need and then plug in your numbers, or you can plug in your numbers here and solve for the variable you need. It's the same math, whichever one you're more comfortable with. Here's a sample. First thing to do, these are all word problems. Word problems throw people to the wayside, okay? First thing you do is take stock of what you're given and where you're trying to go. In our equation, there are 4 variables. We have to be given 3. If we're not given 3, we cannot do it. So your first goal is to find out which 3 we have, okay? So the first number there is 2.0 liters. Which volume? Is that our starting volume? That is our starting volume. It says 2.0 liters of gas is decreased from. So we're starting at 2 liters. So V1 equals 2.0 liters. Then it says decreased from 1.2 atmospheres to 0.25 atmospheres. What variable is 1.2 atmospheres?
P1.
P1, that's my initial pressure, which makes P2 what?
0.25.
0.25 atmospheres. Now we just plug it in. V1 2.0 times P1 1.2 equals V1 times P2 0.25. Solve for V1. Sorry, V2. Does everyone agree? That is atmospheres. Everyone get the same number? Gas law problems really lend themselves well to checking your answer based on logic. Okay? Pressure went from 1.2 atmospheres to 0.2 atmospheres. What direction should your volume go, up or down? Yeah, Ben.
Shouldn't volume to be liters?
Yes. Thank you. About time for the quiz. So if you decrease pressure, it's going to expand. And volume should go up. And it did. It went from 2 to 9.6. So you don't know that 9.6 for certain is the right answer, but you know it went the right direction. Right? So you feel pretty good about it.
How'd you get that?
Hmm?
How'd you get that?
2 times 1.2 divided by 0.25.
Oh, okay. I put in point two.
Yeah, I put in 0.2 too. Yeah, 9.6.
Another one. If I have V1, let's do it directly into the equation. What is my V1?
455 milliliters.
455 milliliters. Now I said we work in liters, okay? You can either convert this to liters, and then your answer will be in liters. But with gas laws, if we start with milliliters, as long as we realize our answer is in milliliters, we can use milliliters. But whatever unit we put in here, we get out here. Okay? So, if that's my V1, what is my P1?
2.50 atmospheres.
2.50 atmospheres equals V2. What is V2? 282 milliliters. So because they are both milliliters, I'm okay. If one is milliliters, one is liters, I have to pick one and convert the other one to it. It doesn't matter which way I go, but they have to be the same. And then the one I'm missing is P2. So we just do the algebra to solve for P2. And what is P2?
B1.
Six things are 3,
3.
4.03.
4.03 atmospheres. I think there's just one more slide on boils. If you get, say you're in Colorado, and you're at a low altitude store in Colorado, and you buy a bag of lightly salted potato chips. You go up the mountain. Why does the bag puff up? Yeah, Ben.
Lower atmosphere, so higher volume.
Yes, yes. So he's doing it by the ratios. Pressure, atmospheric pressure is low at the top of the mountain, so volume goes up. How can you explain it in terms of gremlins and forces and things like that?
Is that being more gremlins inside the bag?
The number of gremlins on the inside of the bag didn't change, but the number of gremlins pushing in on the outside of the bag did go down because you're at a lower pressure. What does the lightly salted affect here?
Tastes better.
Nothing. Okay. Be thankful I'm not one of the professors that puts all this crap in your exam questions, because there is a professor in the natural sciences department that I know does that. He puts all kinds of weird stuff in his problems to fool you. Okay? I don't do that. Okay.